In this final video on the binomial theorem, we're going to make the connection between Pascal's triangle and using binomial coefficients. So Pascal's identity that explains the relationship between combinations and Pascal's triangle goes as follows. Let n and k be positive integers, with n being a number that's greater than or equal to k. Then the following result holds. Now, first of all, the reason n has to be at least as large as k is because n is the set size that we're drawing from. And it says that if you increase the value of n by 1 and you choose k of the elements, that's the same thing as from n elements choosing k minus 1 of them, from n elements choosing k of them, and then adding those two things together. So, for instance, if n were to be equal to 3 and k is equal to 2, we would have the identity that 4 combination 2 is the same thing as 3 combination 1 times 3 combination 2. Oh, excuse me, plus these two things added together. So 4 combination 2, if we did calculate that, we would get, let's see, 4 times 3 over 2. I think we get 6. We get 6 there. And 3, there are 3 ways to select one item from 3. There are 3 ways to select 2 items from 3. And so that gives us the true equality, 6 equals 6. I suppose while we were checking this, I think we had just assumed that it was true, that this identity worked. At least in this case, it does. Now, we're not going to go ahead and prove this here. We're just going to show how it relates. We're going to assume this to be true. We're going to show how it relates to Pascal's triangle. Well, if you think about what 4 combination 2 is, 4 combination 2 is what we're claiming to be. If we look at this table, we're saying that this first element here is the result of taking 0 items and choosing 0 of them. That might seem counterintuitive, but there's only one way to do that. You don't choose any items. How many ways are there to choose 0 items from 1? Again, there's one way. You don't choose anything. And there's one way to choose 1 item from 1 item. That's done by just choosing that 1 item. And so if we believe that this is the connection between these, then at some point we have to say, well, how do we know that it's going to continue on forever? Well, Pascal's identity allows us to establish that. So for example, 4 combination 2, that's this value here. That's for n equals 0, n equals 1, n equals 2, n equals 3. That's the 5th row, so that's for n equals 4. And again, this is analogous to saying from 4, if we have 4 factors of x plus y, then from those 4 factors, we can draw 2 y's, and there's 4 combination 2 ways to do that. Now, what we're claiming here, at least in Pascal's triangle, is that another way to get that value is if we sum these 2 values together here. Well, that's the same thing as taking 3 plus 3, which is equal to 6. And so there's our connection by Pascal's identity. It shows that if we add these 2 combinations together, where notice that the only difference between them is that these both draw from the previous row. This is the previous row. This is the next row. So if n equals 3, then n plus 1 is 4. And so these 2 values added together produce the same value as what's in the 4th row. Choose k of those items. And the same thing goes for down here. If we add 6 choose 4 plus 6 choose 5, that's the same thing as 7 choose 5. So 15 plus 6 gives us 21. And this beautiful identity connects the Pascal's triangle with these binomial coefficients that we're claiming were in fact valid for the expansion of x plus y to the nth power. Now, there is a formal proof for this. We'll leave that out of this video because it just requires a bunch of algebra to combine these 2 terms and a bunch of factorials, so we're going to leave that for another time.